going to cover in this particular video is a way to measure how responsive demand is to a change in price. So if we change the price on some commodity, is the demand going to change in accordance, or is it going to resist that change in some way? And the idea here is that we're going to take the percentage change in demand and divide it by the percentage change in our price. So if we change the price, we measure how much the demand changes and compare those percentage changes. Now the percentage change in demand we can calculate by just taking the total change in demand and dividing it by the actual demand that we're talking about. And we're going to divide that by the similar thing in terms of price. But we can rearrange this thing, essentially move this price to the top and move this delta x to the bottom. This is the same thing as writing P over x over delta P over delta x. And it might seem a little weird to write it that way, especially since the delta x was on top in the first place. But this delta P over delta x, as long as we think of delta x as being really small, this is approximately the derivative of P with respect to x. So say this is approximately P over x over the derivative of P with respect to x. Remember that's exactly what the derivative means. dp dx literally means the limit of the change in P over change in x as the change in x goes to 0. If we were to write out the change in P, that would be P of x plus delta x minus P of x, and the bottom is still just delta x. So what we've essentially done is taken a concept and a starting point and turned that into something that basically depends on a derivative. And so we are actually going to focus on this particular value here and give it a name. This is referred to as the price elasticity of demand, or just elasticity of demand. Remember that our formula there was price over demand over the derivative of price with respect to demand, and we give that a fancy letter. This is a Greek letter called eta. It looks kind of like an N, but it kind of the tail is a little longer. So if you're not used to it, it can be a little hard to pick it out from a regular N, but that is the letter that's used for this. And this is the definition that we are going to be using. Now, what does this actually mean? What is the point of this? Well, the point lies in the formula for revenue. If we look at the revenue, which is just the demand times the price, and without putting in a function for P in terms of x and just differentiating this to get the what we call the marginal revenue, dr dx, keep in mind that P is going to be treated as a function of x even if we don't have a formula for it. We go ahead and use the product rule here. Product rule says that we take the derivative of x, we get a 1, but we leave the P alone. Then we leave the x alone and instead differentiate the P. So we have dp dx. If we want to compare the marginal revenue to 0, watch what happens. So I'm going to start with, let's say in a situation where the demand is very responsive to change in price. In that particular case, dr dx is going to be positive because an increase in our demand, the increase in number of things that we sell, should correspond to an increase in revenue. That's what we'd like to have. We want to sell more items and get more revenue from that. So in that particular case, dr dx is positive, which means that from our formula, we have P plus x times the derivative of P is positive. If we go ahead and solve this, or move stuff around, we're doing some algebra here. P is bigger than negative x times dp dx. and then we want to divide by x and dp dx. Now, one thing to note here, dp dx is negative, because when we actually talk about demand, we always have a particular graph in mind. We always have something where a higher price corresponds to a lower demand, and a higher demand corresponds to a lower price. We always have something like that. It's not always a line, but a lot of times we draw with a line. And a lot of our situations we actually assume it's a line. But the main important thing is that this derivative has to be zero. It has to be a decreasing function. Therefore, when we divide by dp dx, we also need to change our inequality sign. Remember, multiplying or dividing an inequality by a negative has to switch to the sign. The x here is a positive value. We're definitely not selling a negative number of things. So that means that p divided by the x, and then we also divide by dp dx, is now less than negative 1. Well, this side over here is just the elasticity of demand. That means our eta is less than negative 1. Now, since eta is always going to be negative because the derivative on the bottom is always going to be negative, the price and the number of units is always positive, and the dp dx is always negative. So these are always negative, except in some very weird cases. A lot of times we're just going to go ahead and put absolute values here. We're going to say the absolute value of eta is instead bigger than 1, because eta itself is less than negative 1. So absolute value of eta being greater than 1, it corresponds to dr dx being positive. The book refers to this as the demand being elastic. This is when the absolute value of eta is bigger than 1. It corresponds to dr dx being positive. On the other hand, if we look at the absolute value of eta being less than 1, that corresponds to dr dx being negative. We could have actually started with dr dx being negative, had the less than 0 here, and then gone through and we essentially swap all these inequalities. The actual work there, the actual algebra there is exactly the same. But we refer to this one as being elastic and this one being inelastic. In this particular case, selling more items actually causes a reduction in the amount of revenue that you get. And then the edge case here, when the absolute value of eta is strictly equal to 1, we just say we have unit elasticity. This is kind of, the unit elasticity here plays more of a role of like critical points. It's not really a state that you stay in very much, but it is kind of a boundary between these two situations, and that's why we care about it. But let's actually work some problems about the elasticity of demand. I'm going to work on problem 33. In problem 33, it says the demand function for a product is modeled by P equals 20 minus 0.02x, where x is between 0 and 1,000. In other words, they've actually even given us our feasible domain of 0 to 1,000, where P is the price per unit in dollars and x is the number of units. In A, they want us to determine when the demand is elastic, inelastic, and of unit elasticity. Basically, this particular situation can be elastic and inelastic at different values of P and X. It is not dependent on the whole thing being always elastic or always inelastic. And we're going to determine where it is one or the other by determining where its unit elasticity. So we're going to start by just finding the elasticity of demand for this particular case. Now our formula for elasticity of demand does require us to know the derivative of P. So what is it, dP dx? That's actually pretty simple to find here. The 20 goes away when we differentiate, and just the thing in front of the x sticks around. We get a negative 0.02 for our derivative. And notice that this is a negative value. That's what we expect to have. So we find our formula for eta. Remember, that is P over x over dP dx. P here is this formula here. X just stays as it is. And then we put in our formula for the derivative. So we have 20 minus 0.02x divided by x, and also divided by negative 0.02. Now we can simplify this. For one thing, we're going to have 20 over x. Actually, let's go ahead and do this step by step. We have 20 over x minus 0.02. Because that x goes away. We're still over negative 0.02. And then we'll go ahead and divide all this by negative 0.02. Of course, that makes this part here plus 1. That part is nice and easy. This part over here will still have the x on the bottom. We will have a negative. And what is 20 divided by 0.02? Turns out it's 1,000. So we have negative 1,000 over x plus 1. Of course, when we take the absolute value of this, we're just going to have the absolute value of 1 minus 1,000 over x. We want to compare this to 1 to find out where it has unit elasticity. So where is this thing equal to 1? Well, I don't like the fact that they're doing all this stuff with the absolute values. I don't know why they don't just compare it directly to negative 1, because I mean we're always going to be talking about negative stuff in the first place. Essentially, when this is equal to 1, the only possibility that we're really concerned with here is when 1 minus 1,000 over x equals negative 1. If we solve this, essentially we'll bring this negative 1 over to here. We'll bring the 1,000 over x over to the other side. The 1 plus the 1 from over here gives us a 2. So we have 2 equals 1,000 over x. Multiply each side by x, but then divide by 2. We get x is 500. We can essentially turn this into a number line. On one side, on this endpoints, we have 0 and 1,000. Those are the only things that we care. That's the only range that we want to care about. But we also have this point in the middle. And that's the only place where this actually equals, where the elasticity of demand equals negative 1. On one side, it's going to have to be either always greater than 1 or always less than 1. And on the other side, it will be one or the other. We're going to take test points for each of these intervals. I'm going to look at eta of 250, and I'm going to look at eta of 750. Those are nice numbers to put into these intervals. Now at 250, we end up with an eta of negative 3. Specifically here, the absolute value of negative 3 is greater than 1. So the elasticity of demand, or at least the absolute value of it, is always greater than 1 on this interval. For 750, I end up with a negative 1/3. So we always get an absolute value of the elasticity of demand that's less than 1 over here. So this is the absolute value of eta, is what this number line represents. So I'm kind of trying to use some of the same ideas of what we've been dealing with when we were looking at critical points and like increasing, decreasing, and concavity and all that kind of stuff, but using it in this slightly different context. But what this is saying is that that it is elastic on the interval 0 to 500, specifically not including 500 there. At 500, it is unit elasticity. It's inelastic from 500 to 1000. And its unit elasticity, I'm just going to abbreviate as that, when x is 500. Now, we could also talk about what the price is at these cases. So this is specifically what our x values are. Our price, what are the limits on our price there? Well, when our demand is 0, when x is 0, we have a price of just 20. When x is 500, well, this is 20 minus 10, so we actually have a price of 10. So our interval here is from 10 to 20, not including 10. This is where p equals 10 for unit elasticity. And for inelastic, we have from 0 to 10. It's the other side of it. In part B of this problem, they want us to use the result of part A to describe the behavior of the revenue function. What does it mean for it to be elastic or inelastic? Well, remember, it's not really the revenue function necessarily, but the marginal revenue. The marginal revenue, when we are in an elastic situation, when the eta is the absolute value of eta is bigger than 1, then our dRdx, our marginal revenue, is positive. In the inelastic case, that's when our marginal revenue is negative. Or you can say, we can interpret this for the original revenue function r, when its derivative is positive, we can say it's increasing. In other words, what we're saying there is that increase in the number of units sold results in an increase in revenue. For the derivative being negative, it's decreasing, which means that increase in the number of units sold actually results in a decrease in revenue. Again, unit elasticity is just that edge case that we use to actually find the elastic and inelastic parts. You can say at that particular point we do have dRdx is equal to 0, but that's only at that one particular point. If we move a little bit away from that point, we're actually going to be in one of these two cases. So I don't really want to say it's increasing or decreasing there at all. But technically at that point, dRdx is exactly equal to 0. Let's do another problem. Let's do problem 37. In problem 37, they say that the demand for a car wash is, they actually give us a formula for this. We have x is equal to 900 minus 45p, where the current price is $8. So $8 is our current price. Can revenue be increased by lowering the price and thus attracting more customers? Use price elasticity of demand to determine your answer. So basically they're asking here is if we actually lower our price and get more customers, are we going to increase the amount of revenue that we have? Now, one thing to note here is that the formula they gave us for our demand function is actually the opposite of what we normally have. Normally, we have p equals some formula in terms of x. Here we have x as a formula in terms of p. That doesn't actually matter too much here. All we need to do is solve for p. So I bring the 45p over to the other side, subtract x to the other side. I divide by 45. I get p is equal to 20 minus x over 45. So basically the same equation, just do we solve for x or p? We do need to differentiate p because we are going to be looking at the elasticity of demand, and that's in our formula. Of course, when we differentiate p with respect to x, the 20 goes away, the x here goes away, and we're left with a negative 1 over 45. Our elasticity of demand, eta, Remember that the formula there is P over X over the derivative. P is this formula here. X is just X. And then the derivative is negative 1 over 45. In other words, I'm going to actually bring this up here, multiply everything by negative 45, and I'm also going to divide everything by x. So we get 20 over x minus 1 over 45, or in other words, our eta is negative 900 over x plus 1. However, we do know that the current price is $8, so we could actually figure out what this particular elasticity of demand is for this particular case. Now, we do need to know what x is. In fact, x is the one that is in our formula. We're going to go ahead and use our original equation and find out what x currently is. So x is going to be 900 minus 45 times the 8 that we have. Let's go ahead and use a calculator for that. We get an x of 540. So our current price was $8, and we're washing 540 cars. Eta at 540. Go ahead and stick that into our formula. Get negative 900 over 540 plus 1, and we get a negative 2/3. Simplifies pretty nicely, in fact. Now, we do need to take the absolute value. Where the absolute value of eta in this particular case is 2/3. Since 2/3 is less than 1, what does this mean? Well, we define that to be inelastic. That was the situation where we're inelastic. That's the case where dr dx is negative. That means that if we actually attract more customers, if we have more customers, we will have a decrease in revenue. So lowering the price is going to attract new customers, but that's going to result in less money overall. And that's the way all this stuff is kind of used. If we have some way of modeling our revenue with respect to price, or vice versa, we can figure out whether or not we should actually increase or decrease our production, or increase or decrease our price, or however you're going to control that, and see, are we actually going to get more money, or are we going to get less? In this particular case, we probably shouldn't lower our price. In fact, we probably should raise it. All right. But that's where we're going to go ahead and leave this section for now. In the next few sections, we're going to move away from these applications, talk more about graphing functions using the techniques that we've actually used, we've developed over the course of this chapter so far, and we'll graph, well, any sort of function that we can know how to differentiate, at least. So I'll see you guys in that next video.